it's a pleasure to present this mission, of which I am the co-I. This was selected together with ACCESS, an X-ray probe by NASA, more or less last autumn, and the final selection will be in 2026. This is the probe far-infrared mission for astrophysics. So why do we need? So what is PRIMA and why do we need to observe in the far-infrared? Well, first of all, there is nothing planned in this wavelength range in the future, and is a critical gap between James Webb and ALMA. So there's nothing between 25 and 400 micron. And so we really are missing a crucial part in the spectrum of galaxies, stars, protoplanetary disks, etc. So the goal of PRIMA is to fill this gap with the sensitive instrumentations, either in spectroscopy and in photometry. So PRIMA was proposed to NASA. This was the first time that there was this kind of mission. The probe explorer Apex is a size that is intermediate between a small and a large mission, and it is supposed to fly, if selected, at the beginning of the 2030s. So is currently in phase A, and the final selection is expected in late 2026. The PI is Jason Glenn of Goddard, JPL, and the project scientist is Mark Bradford at JPL. The science lead is Alex Pope. These are the co-I's, and there are two co-I's, Italian co-I's, Anna Di Giorgio, that will take care of all the electronics, the warm electronics, and the control system, and myself that are more involved in the science. So first of all, why do we need to observe in this wavelength range? Well, there are now, because many people say, why do you need to observe in the far infrared? There is James Webb. Well, James Webb is doing fantastic discoveries, but is not observing in the far infrared. And the fantastic discoveries, for example, in the extragalactic field, like little red dots, is amazing, but if we don't observe in the far infrared, we will never know what these guys are, because from the spectra, we know that there are broad lines, but this is debated because there are people that say that with very young and hot stars, you can produce these lines. ALMA is not detecting them, so there's no cold dust emission. So we really don't know why there is this rise in their spectra, and whether this is dust heated by an AGN or by stars, because we really miss this part of the spectrum. This is just one of the many cases. So James Webb is fantastic. ALMA is doing fantastic things, but we really miss something in between. So PRIMA is responding to the Astro 2020 Decadal Survey, and in particular to the three main questions: tracing the astrochemical signature of planet formation, measuring the formation and build-up of galaxies, heavy elements, and interstellar dusts, and probing the co-evolution of galaxies and supermassive black holes across cosmic time. So these are the three main themes on which the PI science is concentrated. So the origins of planetary atmospheres, the evolution of galactic ecosystem, and the build-up of dust and metals. And we will address these three topics by observing either in spectroscopy and in photometry. So what is PRIMA? PRIMA is a 1.8 meter aluminum telescope cooled down to 4.5 Kelvin. So we need cryogenics to keep the mirror cool. And it is composed by two main instruments, PRIMAger, that is an imager and polarimeter, and PHIRAS, that is a spectrometer. PHIRAS will be fantastic because it will provide, as we will see soon, spectroscopy over the whole wavelength range between 24 and 235 micron. So will provide a lot of far infrared fine structure lines that are crucial to interpret the nature of the galactic and extragalactic objects. PRIMAger will observe in hyperspectral imaging between 25 and 80 microns, so very narrow, many narrow bands, plus R equal to 4, imaging and polarimetry between 90 and 260. This is a PRIMAger, that is an European instrument. The imager is built in France and with a Dutch contribution because the SRON is providing the detectors that are made by kids, the kinetic inductance detectors based on the new superconductor technology. So it will observe by scanning in the sky, the longer wavelengths are not overlapped to the shorter wavelengths, so you need to scan a large area of the sky to have both instruments observing on the same time. This is a simulated imager done with PRIMAger of 1 square degree. So PRIMAger is very efficient in scanning very large portions of the sky. So if you, there are many young people that probably don't remember the first infrared images from ISO and also Herschel. Well, this is amazing because it is really a resolution that we couldn't reach before with the previous infrared instruments. The other instrument is PHIRAS and is made at JPL, so it is a US instrument. And it will cover the whole spectral range in 2 shots, so band 1 and band 3 simultaneously, and band 2 and band 4 simultaneously. So you can choose just 2 bands or the 4, and in 2 shots you have the whole spectrum. This is an example of a simulated spectra of a very bright galaxy, but at redshift larger than 4, is a redshift almost 5. And you see that we are expecting to see the PIHs at those redshifts and spectra with less prominent features. So it will be really open a new window in the detection of dust up to high redshift. The detectors are KIDS, as this new technology of arrays that is, although the spectrum, the mirror is small, is relatively small, because Herschel, for example, was 3.5 meters, this is 1.8. But thanks to the KIDS, we can reach unprecedented sensitivities. This is a measure of the sensitivity of the detector as a function of time. And when the superconductor detectors started being developed, you see the very huge gap in the very huge leap towards very high sensitivities. And these are really unprecedented sensitivities that we can reach thanks to this new technology. It will go on L2 as Euclid, for example, or Herschel. And this is an example of how big will be the gain. This is in time to scan 100 square arc-minute survey with respect, for example, to Sophia or also to Spitzer, James Webb, Herschel, but this is similar also in sensitivity. So there is a similar plot in sensitivity. So the sensitivity of PHIRAS and PRIMAger will be similar to those obtained by MIRI and somewhat ALMA. This is PHIRAS, for example, in spectroscopy, 5 sigma 1 hour, line sensitivity. You see how deep we could go with this fantastic instrument. So going back to the three main PI science topics. PI science is how they call the guaranteed time. So this is what we wrote in the proposal, and this is what we will do with 25% of time, because 75% of PRIMA time will be open to the community. So it will be an observatory for the community. Again, these are the three topics, and going a bit deeper in what we will do. So in the origins of protoplanetary atmosphere, you see this amazing picture of protoplanetary disks made by ALMA, and with James Webb you can study the inner part of the protoplanetary disks, with ALMA the outer and colder part. But if you want to study the structure of the protoplanetary disks and study the water and icy lines, you need to observe in the far infrared, and PRIMA will do this. So the idea is this is a simulated spectrum of a protoplanetary disk, and you see how many water and CO lines are in the spectra. So no such complete far infrared disk spectra exist at present. In the co-evolution of galaxies and AGN, well, this is a beautiful picture of the spectra of a galaxy shifted from redshift 0 to redshift 5 with the PRIMA spectral range and all the lines that you can see. And we can use the different lines to study the black hole accretion and the star formation simultaneously in the same objects. And this will be the first time that this will be possible. So we will study the two different processes with different tracers in the same samples of galaxies. We can do with Pyras up to redshift about 3, and then we can study their SEDs with the narrow bands of PRIMAger, and then use the calibrations from lines up to redshift 3. So we calibrate the decomposition of the SEDs made by PRIMAger through the lines, and then to higher redshift we will use the results of this photometric, the imaging in photometry. So we want to study the star formation and the black hole accretion in the same galaxies to understand how for example, these relations, these local relations they work, and for example, the M star and black hole relation, how we could reach the galaxies that we see nowadays. And for example, different models predict different ratios between black hole accretion rate and star formation rates. For example, this is simulations from the Santa Cruz semi-analytic models, and this is what we obtain with the Spritz phenomenological model. So you see that at redshift larger than 1, there is a gap between the two predictions. So we don't know which is the way that we could reach the galaxies and the black holes that we see nowadays. So this is what we want to explore with PRIMA. This is a simulation also based on Spritz of the number of galaxies that we expect to detect as a function of redshift. You see that the very luminous ones can be detected up to redshift 8. The more normal ones will be detected up to redshift 3, 4. So we expect many, many galaxies in the surveys that we plan to do with it in geotime that are 1 square degrees to confusion and 10 square degrees shallower. We expect about 60,000 galaxies down to L stars. So this is a huge value for explorations for GI science, that is archival science, because we will provide to the community the data as soon as we will have analyzed them. And with FIRAS, we will also have the resolution to detect the outflows in OH, for example, up to redshift 1.52. So we will also explore for the brightest galaxies the effect of the outflow on the star formation rate, for example, and we will measure outflow velocity and mass, and we will explore this OH doublet absorption feature in the brighter galaxies. So the third topic is the buildup of dust and metals, and the mid-infrared spectra provide crucial diagnostic of dust properties and metallicity. So we will study through the far infrared fine structure lines and PAS, PIHs. We can study the metallicity and the PA versus metallicity relations up to high redshifts, and also through the polarization, we can study the different dust properties. This is an example of the PA versus metallicity relation. This is local. This is what we expect by shifting the mass metallicity relation to redshift 2, and this is what we want to explore with PRIMA. And using the different far infrared fine structure lines and ratios, we can, in detecting them in galaxies up to redshift 2, we can study how this relation evolve. And moreover, by studying the polarization, we can distinguish between different dust production models. So to conclude the part regarding the science, the general observer and guest investigator potential will be huge, provided by these surveys that we will, by the PI science, but don't forget that 75% of time will be open to all of you. So all your ideas. So I have concluded. Probably I am ahead of time. I went too quick, too much, but I am open to questions. So if you want to learn more, please go to the PRIMA webpage at Caltech. There is a newsletter. You can sign up on our website and you can receive the newsletter. And plus there are monthly talks that you can listen from Zoom. So you can connect it. It's at 6 p.m. The fourth Monday of each month. And finally, if you are interested in getting involved, you can join a science working group. We are now building up new working groups because the first ones were limited because we had to do very quickly for the proposal, but now we are looking for new ideas and new people that want to contribute. We are going to publish a new geo book, the volume 2, because we are on archive. There is already volume 1. And so if you have an idea, you want to develop a science case for PRIMA, please provide it and be an author of the geo book. And plus, if you're interested, you can attend the community events. We had one last week in Marseille. It was the first PRIMA European science meeting, and we will have another one in Pasadena in May. It is also possible to follow it remotely. And plus, there will be a PRIMA special session at IAS in Ireland in June. So if you are interested, please follow us in all these channels that are available to you. Thank you. I'm open to questions.
Thank you very much for being on time. So please ask questions. Any questions for Carlotta?
Giorgio.
Ah.
You didn't say much about polarization and polarized light, for example, for AGN science, the possibility to measure degree from the tones, for example.
Yes, it's something that you can investigate if you are interested. I am not really an expert in polarization. There are, for example, Mathieu Betterman is studying the polarization in galaxies. I think not very high redshift, but to cosmic noon is possible. And of course, is a possibility. If you have an idea, you can, I forgot to tell you that in the PRIMA web page, there is also an exposure time calculator. So you can just choose between FIRAS and PRIMAger and just try to play and see whether your case is feasible or not in a reasonable amount of time. Marcella?
Sorry, I missed the spatial resolution of the PSF was in a table.
I don't think there, I don't remember whether there was a table, but the spatial resolution is not great because it's diffraction limited. Number. I think that at 60 micron is similar to 24 micron speed. So.
I don't have
A few arc seconds.
few seconds.
Okay. See, yeah, spatial resolution is not something that we can give as a winning point. This is more the sensitivity and the scanning. Is a survey mission more than a pointed observations. So the spatial resolution is not the winning. The selling point, because it's far infrared and the mirror is small.
Okay, if I can add, I mean, at 24 micron, it's not so bad because it's less or around one arc second. 24
Yes,
micron.
24.
So you can use, let's say, the mid-infrared in order to blend planetary. This is the idea if you want to do a survey.
Yeah, the idea is to go stepwise, starting from the shorter wavelengths to the longer, of course, where we will be also confused, probably at very high sensitivities, and then use step by step, filter by filter to deconvolve and blend the sources at longer wavelengths. But yeah, I have in mind this 60 micron, the same resolution as 24 micron splits.
Roberto?
What is the field of view?
The field of view, the smaller one that you can get is 10 arc minute by 10 arc minute. If you want to have both instruments covering the same area, is 10 by 10, and I think that the overlapping area in 10 by 10 is 4 by 4. But it's very, very fast. You can cover large areas very easily. Yes,
Please.
Daniel?
I believe that the imager in PRIMAger, they are tunable filters, right? Or
I'm not sure they are tunable, but I think they have not decided yet how narrow they will be. No, I probably went to. So it's still possible to change the central wavelength because they have not fixed it. This is what I understood. But yeah, I'm not completely sure about it. But for sure, this is the range is fixed. Is not what is not fixed is the narrow bands.
the narrow bands? Because
Yeah.
that would be very important to target the specific features at different redshifts.
Yes,
Be observing the same.
you're right.
Other questions? I might have this.
No, there is not.
Right.
Two questions. One is
The galactic center region can be observed, but is the saturation in
I don't think is something that we plan to observe the galactic center, but it's not in the PI science for sure. It depends on the constraint on the L2 and the instruments. I admit I don't know.
I don't know if maybe you mentioned it, but what's the estimated cost? And what's the plan for launching it? Like even all the Euclid issues, the Russians or SpaceX, is there a plan already?
The estimated cost is fixed by the Apex call, and is $1 billion plus maximum 30% contribution from the other countries. And we are providing something. The French are providing the instruments, the Germans are providing the steering mirrors. So there are contributions, but they cannot be more than the 30%. The plan is to launch it at the beginning, is 2032 with the Ball Aerospace. I think should be. Is written somewhere? Yeah, but I don't think that it will be Elon Musk if they are not changing everything, and we don't know.
Other questions? I might ask one. So what are the key synergies with like that in the PI science are already mentioned, or at least like planned with James, like on the James website, but also on the ALMA. So like what are the let's say for galaxy evolution, obviously I'm asking. So like is it?
Well, there are, I think that mainly in the PI science, we just mentioned, for example, what I showed for the protoplanetary disks, that you just observe different parts of the disk at different wavelengths. So the three of them are all important and complementary. Regarding galaxies, for example, as also Francesca showed at the Marseille meeting, for the dust temperature is very important to have ALMA, because you need to sample also the Rayleigh jeans, tail. So there are many synergies in any of the fields because the wavelengths are complementary. So we really need to observe all of them. Yes.
Thanks, Carlotta, for the presentation. So regarding the plot we were showing from Casey, the SED of little red dots. So
yes,
in this work, they estimated that the far-infrared emission of these objects, the redshift around 5, 6,
yes,
is expected to
is
be
6.
Exactly, is expected to be 10 to the 10 solar luminosities. So if I
this is what they expect based on the non-detection of ALMA.
Exactly. So the total far-infrared luminosity is expected to be something like 10 to the 10 solar luminosities.
Yes.
So you were showing the plot before. So is really this a science case that PRIMA can address? Because you were showing that at redshift.
Probably not at redshift 6 or 7, but at redshift 3 or 4, for sure. Yes.
Okay, so not really.
Maybe not these extremes, but there are little red dots also at redshift 3.5, 4, and
okay.
And also in this in the shorter wavelength bands, probably PRIMA can do something. So even if you see that this rise is going down, this is a constraint that is important. I mean, even if you have a non-detection here, or you have a detection here, this
Sure.
will tell something.
Sure.
This is something that we need to calculate and to play with the exposure time calculator. For example, Ivan did some calculations, but what we expect is that for the smaller redshift and probably the shorter wavelengths, PRIMA can help.
Okay. So where is expected in particular those rise?
Yes, exactly.
Especially through stacks.
Okay.
You stack, everything help.
So the 1 square degree survey, if you should stacking with it.
Okay.
Even a Cosmos Light survey should be able to go below the total rate.
Okay, that was.
Okay, let's see if there are questions online. I don't think so, because I don't see. Right. Yes. Please. Yes, you can talk. I see a
Okay, hello. Can you hear me?
yes.
Okay, great. Thank you for the very wonderful talk. It's very interesting. It's very inspiring. So I have two questions. So first question is very easy. So what's the expected lifetime for PRIMA?
The nominal lifetime, that is the shortest possible, is 5 years, but we expect at least 10, because the cryo coolers are the same that are mounted on MIRI, and so they are not big tanks of helium, so they will last more than the previous infrared missions.
Okay, thank you. That sounds great. So the second question is about the PRIMAger. So it has a hyperspectral mode with a resolution around 10.
Yes.
I'm a little bit wondering what's the major science goal of this design.
The major science goal of having these narrow bands, you mean?
Yes.
Is that they will be sensitive to the features, for example, the PIHs. So you can distinguish the PIHs from the continuum, even if you don't have the spectroscopy, for example, at high redshift, at a redshift larger than 3, where FIRAS cannot measure the spectra.
Okay, I see. Okay. So because it has a little bit overlap in wavelengths with FIRAS, maybe I was wrong, but
The
I
overlap
just thought
of FIRAS is complete, because they are observing on the same wavelengths, but one in spectroscopy, the other in photometry. Is called hyperspectra because it is a sort of spectrum with R equal of 10, but it is an imager. So if you want to integrate on a larger band, you just integrate over 3-4 channels, for example, and you get a lower resolution, but a higher sensitivity.
Okay, I see. Thank you very much.
You're welcome.
Thank you, but
So there are a lot of filters.
Yes,
Okay.
a lot of narrow filters. I show. When I show the SCD, yes, these are the filters. So there are 4 in polarimetry at longer wavelengths, longer than 90, and then there are these narrow ones that are not totally fixed, but there will be many narrow filters between 24 and 90 microns.
okay. So let's thank Carlotta again.